Hello everyone, my name is Mark. Before I get started, I want to give a very sincere thanks to the conference organizers for giving me the opportunity to give this presentation via video. I'm really sorry that I couldn't attend the conference in person this year, and I hope that I'll be able to see some of you at next year's conference. So with that said, the presentation I'm giving is solving k-1 stable instances of the k-terminal cut problem with isolating cuts. So first things first, we need to define the problem itself. In the k-terminal cut problem, we're given as input in a weighted, undirected graph G, and we're given a set of k distinguished vertices, which we call the terminals. And what we'd like to do is partition the graph into what we call source sets, such that each source set contains exactly one terminal, and the total weight of edges that go between source sets is minimized. An equivalent way to think about this is we are removing edges from the graph such that the terminals become disconnected, and the minimum k-terminal cut problem is how do we remove a minimum total weight set of edges such that the terminals get disconnected. So just to give you an example, here on the left-hand side, we have an example input for the k-terminal cut problem. And on the right-hand side, we have the optimal solution. Now, I'll just point out that there's another feasible solution, which is to remove these three edges of weight 3. If we did that, we'd be removing a total weight of 9. But the minimum weight we can remove that disconnects all the terminals is these 4 central ones to remove a total weight of 8. Now there are two things that I'm going to need to define in order to define tell you about our contribution. The first is the notion of gamma stability, and in order to define that, I need to talk about gamma perturbations. So if we have one of these instances, a weighted graph, we'll define a gamma perturbation of it as multiplying each edge in the graph by some factor up to gamma. So that can be a different factor for each edge in the graph, but essentially you go through the graph and you're allowed to multiply each edge by something up to gamma. Now an instance is said to be gamma stable if the optimal solution, the set of edges that you remove in the minimum k-terminal cut, remains optimal for every gamma perturbation of that graph. And just to give a little bit of intuition, every 2 perturbation is also a 4 perturbation. Therefore, if we have a graph which is 4 stable, we know that it is also 2 stable. So just to give you an example of this, let's say that we took this graph. On the right, we have a 1.1 perturbation of the graph. And it turns out that in this perturbation, the optimal cut is still the cut that was optimal in the original graph. So in this case, this doesn't entirely prove that the original instance is 1.1 stable, but intuitively you might have the intuition that the sort of worst gamma perturbation of a graph is the one where you multiply all the edges in the optimal cut by gamma and leave the rest as they are. And indeed, that's what we've done here. The optimal cut remains, and so it'll turn out that this instance is indeed 1.1 stable. Now, I caution against just looking at the best cut and the second best cut. This is a trap that you could fall into with gamma stability. So if we look at this graph, the best cut has a weight of 3, but there's another cut that has a weight of 21. Now, if we looked at that, we might naively say that the graph is 7 stable. And indeed, it is 7 stable, but in fact, there's a better stability result we can get. What we could do is we could multiply both of these edges by 9, and in fact, we would see that it still remains the optimal solution because 27 is a better cut than 29. And the reason for that is because this edge that they have in common, this edge of weight 9, gets multiplied by gamma in the optimal cut and also in this sort of alternative cut that we want to become the optimal cut in the perturbation. So we need a slightly different statement that discounts the edges that they have in common. And here's the statement. An instance is going to be gamma stable if for every alternative cut, the edges which are in the alternative cut but not the optimal cut are at least gamma times the total weight of the edges which are in the optimal cut but not in the alternative cut. So basically discounting the edges that they have in common. So this will come up later. This is a lemma that is useful. But again, the second thing I need to define for you is isolating cuts. So the idea of an isolating cut, for a k-terminal cut problem, there are going to be k isolating cuts, one for each of the terminals in the graph. And the isolating cut is just a cut which separates one terminal from the rest of the terminals. We'll use the notation qi to denote the source set of that cut. I'll return to that notation later and remind you of it. So just to look at these graphs again, for terminal T1, T2, or T3, the isolating cut would be the cut that just separates them from the rest of the terminals by cutting the edge of weight 3. Now, in the case of terminal 4, we actually have two options for the isolating cut. It could be these two edges with weight 2 or this edge with weight 4. Now, if we go over to this example on the right, the isolating cut for T1 just removes this edge. The isolating cut for T2 removes just this edge. And if we want to take the isolating cut for T3, we remove both of these edges for an isolating cut of weight 3. There are two facts that are known about isolating cuts, which will be relevant to our presentation. The first is that if we take all of the isolating cuts except for the cut of largest weight, that we get a 2 minus 2 over k approximation for the optimal k-terminal cut. So it's a very simple approximation algorithm for the k-terminal cut problem. And then if we're given an instance of the k-terminal cut problem, and we look at the source sets of the isolating cuts, then there will be an optimal cut in which the source set of the isolating cut is contained in the source set of the optimal cut. Now, this can be a little bit of a tricky situation when there are multiple possible optimal solutions to the k-terminal cut problem, but in all gamma-stable instances with gamma larger than 1, there's only one unique optimal solution. So what we can say is that for that optimal solution, all of the isolating cuts are going to be subsets of the source sets in that optimal solution. So just to illustrate this for you, if we take a look at the examples we were looking at earlier, and we color the vertices according to which ones are in the source sets of the corresponding isolating cuts, you see that indeed the isolating cuts give us sort of a partial solution to the k-terminal cut problem. Now we don't have any information about some of the vertices. We don't know because they don't belong to any of the source sets of the isolating cuts, but for some of them we do know that which terminal they should belong to in the optimal solution because of the isolating cuts. Now, in this example on the right-hand side, albeit it's sort of a simple example, but it shows us that in certain instances, taking the isolating cuts is enough to recover the optimal solution, and that's essentially what we're going to show, a structural result that we're going to show in this paper. So just to give you a survey of previous work, on the left-hand column we have the progressively better approximation algorithms. There's the first approximation algorithm for this problem was the 2 minus 2 over k approximation, and then it got generally progressively better. The reason that there is one result out of order is because I've actually listed these in order of increasing computational complexity. So this result, even though it's a weaker approximation algorithm, is a simpler algorithm. And then on the right-hand side, we have the stability results. And when I say a stability result, I mean an algorithm which can solve instances which are sufficiently stable. So this result in 2013 showed that you can solve instances which are at least 4 stable, and this result in 2017 showed you can efficiently solve instances which are 2 minus 2 over k stable. And so those are polynomial time algorithms. Now the thing I'll draw your attention to is that the 2 minus 2 over k approximation algorithm is actually the only one whose complexity is that of a minimum cut or anything less than linear programming. All of the other algorithms rely, at least one of the steps includes solving a linear program. So these are kind of hefty algorithms, and the 2 minus 2 over k approximation is a much simpler one. And so what we're going to show in this paper is we're going to show that 2 minus 2 over k approximation delivers an optimal solution on instances which are at least k minus 1 stable. And we're going to show that that's actually the best possible result. We're going to show an instance that's k minus 1 minus epsilon stable, on which the approximation algorithm does not deliver an optimal solution. So here's the exact statement that we're going to prove. Recall that in general, the source set of the isolating cut is a subset of the source set of the optimal cut. And what we're going to show is that in a k minus 1 stable instance of the k-terminal cut problem, this relation holds at equality. So the source set of the isolating cut is the source set of the optimal k-terminal cut. So for the sake of this presentation, I'm not going to go through the entire proof, but I'm basically going to give you what I think are 3 key ideas. So if there exists a counterexample, there must exist a minimum possible counterexample. So the first thing we're going to do is consolidate down to a small instance of the problem, which there must be a counterexample. And then we're going to explore comparing certain alternative cuts to the optimal cut using the condition we derived earlier. And that's going to give us a set of inequalities. And then we're going to derive another set of inequalities based on the isolating cut conditions. And what we'll discover is that essentially these two things are at odds with each other. We'll arrive at a contradiction because it's not possible for both of these inequalities to hold. So first, here's what I mean by the minimum counterexample. So let's say we have a counterexample, a k minus 1 stable instance of the problem in which the isolating cuts do not return the optimal source sets. So what we can do is we can divide up the optimal source set. So let's say the optimal source set is all the vertices that are red. We can divide it up into 2 sets. One is the set of vertices that are in the isolating cut, and then the remainder, the ones that are not in the isolating cut. And we can do this for each of the terminals. And what I claim is that we don't really care about what happens internally to these sets. What we're only going to care about is how these the edges between these sets relate to each other. So essentially what we can do is if we have a counterexample, we could consolidate it down into a counterexample where all of these are just one vertex. So essentially we've consolidated, if the counterexample exists, there must be a counterexample that has at most 2k vertices and has this general structure. And note that because we assumed that for at least one of these, the qi is not equal to the whole source set, there must be at least one of these ri which is non-empty. And so the first condition that we look at is we tried to create alternative cuts. And in these alternative cuts, we construct them by putting all of the ri into the same source set. So what I've done here to illustrate the cut is any edge which is cut, I've made solid, and any edge which is not cut, I've made dotted. So these are the edges that are solid are the ones that go between different colors. These are the ones that are cut. Likewise on this side, this is the optimal cut. So this is the optimal arrangement, and these are the edges that are cut in the optimal cut. Now I've colored them black if they're the same on both sides of this inequality, and I've colored them in a certain color if they're different. So black, same, color, different. Orange here is for the edges that go between a qi and the corresponding ri. And then on the right-hand side, the red edges are between a qi and a different rj, or the yellow edges, which are between an ri and a different rj. So what we see immediately from this is that on the left-hand side, we have the orange edges, and on the right-hand side, we have the red and yellow edges. What happens when we look at the isolating cut now? Well, we assumed that the isolating cut, let's say for Q2, was just the set of edges that leave Q2. not the edges that leave Q2 and R2. So because we're assuming that this is the isolating cut, it must be the case that the edges cut here have a weight which is less than the edges cut here. And so in this inequality, we have the orange edges on the right-hand side. Those are the ones that differ on the right-hand side. And on the left-hand side, we have the red edges and the yellow edges. And so there's a fair amount of work that actually goes into finagling this so that all the inequalities work out, because this isn't just one inequality. You can generate k such inequalities here, and likewise you can generate k such inequalities here. But ultimately, the reason that you ultimately arrive at a contradiction is because in one of these, it's orange edges greater than red and yellow, and in this one, it's red and yellow edges greater than orange edges. And so without going into that in much more detail, I'll just say that you do arrive at a contradiction, and so it's not possible for there to be a stable instance where the source sets are not equal to the source sets of the optimal solution, and so we get the statement of our theorem. Now, an immediate corollary is the result I claimed earlier. So if we have a k-1 stable instance of the k-terminal cut problem, and we take all but the largest isolating cut, then that will also return the optimal solution. And the reason that I've stated it that way is because that's the exact same as the 2 minus 2 over k approximation algorithm. So that algorithm, which is based on isolating cuts, is an optimization algorithm for k-1 stable instances. Now there's a natural question, can we do better? The answer is no. The other result we show is that there exists a k-1 minus epsilon stable instance of the k-terminal cut problem where not only are the source sets of the isolating cuts not equal to the source sets of the optimal cut, but in fact they're just the source set literally just equals the terminal itself. So the optimal isolating cut is just to remove all the edges adjacent to the terminal, so we get no information whatsoever about the optimal source sets. This construction, I'm not going to explain how we arrived at it, but I'll just explain how we actually do the computation once we have it. You'll notice that there's a lot that's very familiar. Again, it's a graph with 2k edges. In this case, we have these orange edges going between ti corresponding si, red if they go between ti and a different sj, and yellow if they go between si and sj. There are some nice properties. This construction has a lot of symmetry. So for example, if we just go ahead and compute the isolating cut for one of the ti, then if we show that the isolating cut is just to remove the adjacent edges, then the same turns out to be true for all of the other tj because of the symmetry. Likewise, when we show that the optimal k-terminal cut is to remove the yellow and orange edges, and that holds true even if you multiply them by k-1 minus epsilon, we're helped by the fact that there's a lot of symmetry in this graph. So when we look at alternatives to the optimal cut, thanks to the symmetry, there's not that many that we have to consider. We can enumerate them in a very systematic way. And so because we do that enumeration efficiently, we show that this instance is indeed k-1 minus epsilon stable. So just for some concluding remarks, we showed that in k-1 stable instances of the k-terminal cut problem, the isolating cuts return the optimal source sets. The immediate corollary was that the well-known 2 minus 2 over k approximation based on isolating cuts is an optimization algorithm in the k-1 stable instances. And then, can we do any better? The answer is no, because there are k-1 minus epsilon stable instances where the isolating cuts are all just the trivial cut, which is to return the terminal itself. So as an immediate corollary, there are k-1 minus epsilon stable instances where the 2 minus 2 over k approximation does not deliver an optimal solution. So again, thank you very much for listening to this presentation. If you have any questions, you can email me at marvel@berkeley.edu, marvel@berkeley.edu, and I sincerely hope that you enjoy the rest of the conference. Thank you.